So hi everyone, so today we are going to learn about the elementary profile of a dam. So profile means the cross section of a dam, and that's the elementary profile. As the word elementary means the basic profile that a dam has to have. For example, if this is the base, rather the ground, and the height of water is up to this. Water is up to this height. And this is the head of water, or rather height of water given by the H. Now, to contain this much water or to hold this much water, we have to have a dam here. So the elementary profile of dam, always remember, it will be a right angled triangle. This will be a right angled triangle with height equal to height of water, and there will be some base. So if you see this height you cannot adjust, because the height will be as per the height of the water. If the height of water is increasing, the height of dam will also be increasing. If the height of dam is decreasing, this height will be decreasing. The only thing that you can fix is B. So this is the elementary profile of a dam. Elementary profile of a dam means the basic cross section of a dam that need to be there. This is how a dam has to be there. This will be a right angle triangle with base B. Okay, fine. Now for considering the elementary profile of dam, you have to consider three forces. One is, of course, it's a gravity dam, so it should be having its self weight. And the second thing, as water is there, there will be water pressure. So water pressure will be there acting. And as water is there, water will be seeping downwards and it will be exerting a pressure in the upward direction, and that's called as the uplift pressure. So remember, while considering elementary profile of a dam, only three forces has to be considered. Those are self weight, water pressure and uplift pressure. And this is how it is working. So if I'm going to draw the water pressure, this is how the water pressure is going to act. Here the pressure is 0, here the pressure will be gamma W into H. All will be acting horizontally towards this direction. So this is how your pressure is acting. There's no doubt. And this pressure, this horizontal pressure, the resultant of the horizontal pressure, I'm writing it. The resultant of horizontal pressure, this is water pressure in the horizontal direction. This will be acting at a distance of h by 3 from the base. From the base, it will be acting at a distance of h by 3. And here water pressure will be there. Water pressure, if I'm assuming there's no water at the downstream, I'm assuming no water at downstream. So if that's the case, the uplift pressure at the downstream will be 0. The pressure at here will be having a value. This will be acting like this. This is how the uplift pressure is acting. Here the height of water is H. So the uplift pressure will be gamma W into H. And apart from that, I am giving a constant, uplift constant C. We'll talk about this later, why this C is required. C into gamma W into H. Not directly writing gamma W into H, I'm just putting a constant, or rather a coefficient as C. So this is how it is acting. And see, this is a triangle variation. This triangle variation, this is B. So the resultant uplift force, I don't know where it is, what's the value it is. This is the resultant uplift force. This is a triangle variation, so this will be acting at a distance from this point 2 by 3 times this base. And if I consider the self weight of this dam, the self weight will also be acting downwards for sure. That is the self weight W, and that W will be acting at a distance of 2 by 3 B from the base. So this point is the toe point. So these are the three forces acting and the distance we have marked. Now this is acting, this U is acting at a distance 2 by 3 from the toe, and this is also acting at it. There's one point, there's one point. So I'm writing this as M1 and this is M2. So if I'm putting the distance, the total base is B. So this, I'm dividing this into 3 equal halves. So this is B by 3. This is also B by 3, and this is also B by 3. So this M1 and M2 are the middle 1/3 points. M1 can be called as the inner middle 1/3, inner middle third point, and M2 as outer middle third point. So inner middle third point and outer middle third point, you have got M1 and M2. So that you have got. Now if you see, both this U and W are passing through M1. So the moment of the force W and U1 about the point M1 will be 0. So I don't know what it is. So keep it there as such. So I'll be writing the value of WH, the horizontal water pressure. The horizontal water pressure is a triangle variation that will be half into base into height. So half into base is gamma WH into height is H, is nothing but gamma W into H square by 2. So that is the horizontal water pressure. And the uplift pressure acting, that's also a triangle variation, half into, this is the base, or rather this is the height, or this is the base. This is half into base is B and height is C into gamma W into H. So that can be written as C gamma W BH by 2. Similarly, the total weight of the concrete, W, weight of the concrete, if I am assuming that the concrete is having a weight density, or rather the specific gravity is G, So this area has to be multiplied by the weight density so as to get the total weight. The area is equal to half into base into height. That is just the area that has to be multiplied by the weight density of the concrete. Weight density of concrete, gamma C. But gamma C is equal to specific gravity multiplied by gamma W. So this can be written as G into gamma W into BH by 2. So you've got the value for WH, U and W. You've got that. Now what we are doing is we have to fix what will be the base width. So I have to fix the base width. Your whole idea is to fix the base width. There are two things that can happen. Either what happens, there will be tension towards this point, or rather it will be sliding. So you have to derive the base width for two conditions. The first condition is for no tension criteria. No tension criteria. So for that, what I'm doing is the resultancy. If you have this force, and the resultant will be like going like this. It will be towards the toe. The resultant will be acting towards the toe. So I am considering the equilibrium, equilibrium condition. I'm going to consider the equilibrium condition. At any time, the whole forces and the whole moment should be 0. So the sigma of moment about the point M2 should be equal to 0. So that is the equilibrium condition, because at the point M1 both these two forces are acting, so it won't be having any moment. So that's why I'm taking the about the point M2, because your resultant is acting towards the toe. So I'm trying to find the moment about the point M2. So if about the point M2, if I'm considering this WH, see WH, the distance from the M2 will be H by 3. So WH into H by 3. And that is acting in the clockwise direction, so that's why it's positive. Now coming to the moment due to W, about this point it is having an anti-clockwise moment. So that is minus W multiplied by, this distance is B by 3. Similarly, about the point M2, this this about this point and U. So this is having a clockwise moment. So that's why positive. It is U multiplied by, and this distance is B by 3. This has to be equal to 0. Now substitute all the value. WH we know, W gamma H square by 2 into H by 3 minus weight is G into gamma W B into H by 2 plus uplift is C into gamma W into BH by 2 has to be equal to 0. Now if you take all the terms outside, or rather there are some terms just common, gamma W common, gamma W, 2 is common in every term, then you have some H term. If you cancel out the H term, what you'll get at last is H square minus slight correction here, I've forgotten to write B by 3 here and B by 3 here, so I have to substitute that. So I'll get H square minus B square G plus CB square is equal to 0. So remember, my whole idea is to find the base width. So this can be written as, if I take b square outside, b square into minus g plus c is equal to 0, or rather b square is equal to, if I take the every term to the other side, minus h square by minus g plus c. So if I take minus out of this minus and this minus gets cancelled, so that is h square by g minus c, or rather b is equal to h by root of g minus c. So this is the equation for the base width for having no tension. So for no tension to occur, so this, the whole idea is to, you are fixing the dimensions of a dam. So already you know the height, how to fix the base. So for no tension to occur, the base should be having a distance, or rather the length of h by root of g minus c, where g is the specific gravity of the concrete and c is the uplift coefficient. So next way to fix the base width is by no sliding criteria. We have seen that if we have a dam and it should not be sliding, so the sliding force, we know that it's the horizontal force, and here the horizontal force is your water pressure in the horizontal direction, and your resisting force is your friction, which was given by mu into sigma v. I hope you remember this was the forces acting, and here sigma v means your weight is acting downwards, your uplift is acting upwards, so that is nothing but the weight minus uplift force. And the limiting condition, see, you have resisting force and sliding force. Always we know that the resisting force has to be more than the sliding force, but at the limiting condition, thing that I can say that is your sliding force sigma h should be at least equal to, or rather your should be equal to mu into sigma, or rather your resisting force should be at least equal to the sliding force. This is the limiting condition. So this, the horizontal force is nothing but the horizontal water pressure, and mu into w minus c. Just substitute the value. We know that we have already seen the value for wh. Wh is nothing but gamma w into h square by 2 is equal to mu into weight is g into gamma w into bh by 2, and uplift is c into gamma w into bh by 2. Now this equation also, in every equation you have got gamma w, 2 and h, and if you take it outside, you'll be getting it as, every time you have h, so h is equal to mu into g into b minus b into c. Always I'm saying that your aim is to find the value for b, so take b outside, so it is b into g minus c, or rather I can say b is equal to h by mu into g minus c. So this is the equation that you are getting. So for no tension criteria, you get the equation base width is equal to h by root of g minus c, and for no sliding criteria you get b is equal to h by mu into g minus c. Always remember, out of these two values, whichever is higher you have to adopt that value. Whichever is higher among the two, that has to be fixed as the b. Because if you, for example, if your value for b is 10 meter here and your value is 20 meter here, you have to select always the higher value. That will be giving a protection against sliding as well as tension. So this is how you fix the elementary profile. So elementary profile is always used when we are only considering the self weight, water pressure and the uplift pressure. And remember, the elementary profile is just a right angled triangle.